We're coming to that one too.
Oh, I'm sorry. I'm excited. Okay. Thank you very much.
Yep.
Okay, our next demonstration is going to be in a resting position. The balance spot will not move forward or backward by more than 8 inches over a 1 minute interval. Okay, now the problem with this is that we specified on our specification that it was a smooth level surface. Now I'm guessing that the stage is not completely level, and the smallest amount of variation in weight distribution or an angle on the balance spot will cause it to drift. So we're going to try and see if we can find a level spot, but it may not.
Yeah, probably is. It's been drifting all over the place. One of the things that we never thought about, the motors themselves are 7.5 pounds a piece. But if I take my wallet, it's drifting one direction right now. I put my wallet on it. Might not be enough.
Chris has got a big wallet. Yeah.
He has no money.
Right. But if you put a little bit of weight on the other side, 2 wallets and a roll of tape is enough to make it. So trying to balance it every day, we tried to balance it, and then we moved to a different part of the room and it would be off, and we'd shut it off and turn it back on, and the wire had shifted, and it would be off.
We did find a few spots in the senior design lab where it barely moved at all.
And now with some weight on it to help counterbalance it, it's a little better. But I can't sit here with the remote and keep it in between the lines. This spec actually came to competition. You're supposed to do a 20-foot obstacle course, stop, turn around, and come back. And the stopping for 10 seconds is where we came up with this. The models looked a lot better than the real thing.
Okay, and as we specified, there's 2 E-stops on the robot. I specified about the competition. One of them is this switch here, and one of them is this transceiver that after we already demonstrated that if you shut this off, it'll stop within 2 seconds.
Take the wallets.
The next requirement is that it stops within 4 seconds. So after 2 seconds, it's stop.
And obviously, if you cut power to it, those switches are the main power of the batteries.
Okay, and in spirit of the competition, since we're supposed to make a predetermined obstacle course, we can make anything we want for the balance spot to go over. We didn't really get to that point yet, but we figured we'd do some dowel rods or wires or something, a little bit, some obstacles to show that we could do this.
They're not big, but it's something. I think Greg wanted to see it go up one of the ramps in here. I don't know if we can do it or not. How much torque we have. I don't know how the ultrasonics will handle it, but we can try it.
Binders earlier and it didn't work out.
See if you can go
See if you run up to the top of the room.
We can give it a shot. Like I said, we got it working a couple of days ago.
The only time we can do
We just want to push it. Once it works, you can hear it a little bit. The other one?
Yeah, we never tried it on carpet.
Yeah, I've never tried carpet, so I don't know how to handle this. Yeah, like I said, not much torque on these new motors. That little implant right there is just too much for it. It starts trying and it just... Well, that's a dramatic failure.
That's going to have the courage doing that.
Comparison, I do, real quick. A little bit of show and tell here. I brought our old motors. These little things actually put out more torque. You're going to see the new ones. They're much bigger. They look heftier. They're designed to run faster. This puts out more torque. The torque constant, 200 ounce-inches per amp. On those motors, 70 ounce-inches per amp.
Wow.
So a big loss when we couldn't use these anymore. But you come up and play with it, there's a little bit of wiggle in the little bit of feed backlash, thank you, in this motor. When you put the wheel on it, and you put that big tall platform on it, ends up being 7 or 8 degrees that just was too much.
Any questions?
Since this is a commercially available technology, how does yours differ from what is available?
Well, that was part of what we said in the beginning. We built almost everything on this. So like I said, some of these other teams are solving more complex problems, in some cases different kinds of problems. You know,
Did you use any reference to the existing technology to do your project?
not really. Most of ours goes back to first principles. If you look at our paper, we've got a model, we've got a physics model built up. We did get some equations for modeling it from one of the ME profs. You did some reading on motor current sensing, but we basically designed
So
everything.
you would know whether you're using the same technique as Segway?
I know the Segway uses gyroscopes, which we thought about, but in the interest of time, and this worked, it was simpler, we decided not to do that. So I know we're not using the same technology as them.
More?
Could you elaborate more on how you were able to basically detect the amount of torque on the motors and everything? And did you guys use a circuit? Was it a processor that you used?
It was the whole current sense circuitry that I explained in the power diagram, and then extended one further within the software diagram. We use the current sense resistor, which is a known resistor value, and we measure the voltage across that and find the current, since torque is proportional to current. You can feed that information in the processor, and then it can supply the current.
Okay, so you're reading the torque off of the motor.
We actually ended up with 4 ADC readings. We've got 1 resistor for forward and 1 resistor for backward on each motor. And then, because of noise in the system, we actually have to sense both the high side and the low side is tied to ground. But because of the wire lengths, and we're dealing with so much current, it doesn't sound like 10 or 15 amps is a lot. But for a system like this, it's actually fairly significant. We're dealing with 50 millivolts across that resistor. A small change on the low side, on the ground side, is significant. So we ended up with 4 readings going into the op-amp circuit and then feeding the ADCs.